So we start this. We start, kind of reviewing from where we were yesterday with the derivative of exponentials and derivative of logs that are not e and not ln, right? So just a quick recall. Recall that if y is equal to a raised to some function, that the derivative of that piece would be y prime equals ln a. I'll put that in parentheses. You probably don't have to. And then you kind of have this, I think yesterday we were doing it like this, where you're leaving that space for the derivative of the f of x, and then you basically just copy and paste this whole thing, right? And then what goes here is simply the derivative of that piece. Does that make sense? And we also said that if we had y equals log base a of f of x, that what you would get for that is y prime is equal to f prime of x over ln a, and then whatever this piece was would copy and paste from here to the bottom. Everybody recall that? So those are kind of the two driving things that are going to take us to where we're going with this problem. Now the thing is here, we're not going to copy and paste this piece yet. All right, because the first function we got to deal with is the 5. So we got to figure out, that's going to be straight power rule. The 5 is going to come down, we're going to drop it by 1. Does that make sense? So the first piece of this is going to be 5, then all of this raised to the 4th. Does that make sense? But now we have to, kind of take the derivative of this inside part. Does that make sense? So the derivative of the inside part is, you forgot it twice. But it is ln of 2. Do we agree? We got this piece. And then we're going to have kind of a space, right? And then we're going to have this piece, right? But what goes in this space here? What goes in that space? And the answer is 3. You forgot, and I'm not trying to be a jerk, but you forgot to do that second chain rule. And that's what happens, right? You get chain rule kind of embedded in chain rule, kind of embedded in chain rule, and it's really hard to kind of keep up with, what have I taken the derivative of? What do I got to take the derivative of still? And so the answer that you would get for that first piece, to simplify it, would be 3 ln 2, 2 to the 3x. Does that make sense? Now, to deal with the next piece, what would the derivative of that piece be? And I'm pointing at the screen like those of you watching at home can see it, but I'm pointing at it, damn it. What's the derivative of this piece? Well, it would be, if we think about it, it's the ln of 3. That was that first piece, right? That piece shows up always, right? And then this whole piece is going to show up. And I'm going to leave some space there. Just move it down. All right. So ln of 3, that whole piece, and then what's going to go in the middle here? And what goes in the middle of there is 2. So the final answer will be, we'll just move the 2 out front, and that will be your final answer. We'll bring that parenthesis in. And that's your final result. That is tough. That is very tough. You did pretty good, except to get the 3 and the 2 out front. Okay. Like I said, that's got, power rule in it. Layers. Yeah, very much layers. My man Marine Bill would say there are a lot of landmines in there. One false step and you'd lose a leg. All right. Any questions on that? Now, as we go through this process of the next one, what's going to happen here is, I think everybody understands that the element of 7 is going to be on the bottom. The element of 7 is going to be on the bottom, right? Then this whole thing has got to go to the bottom. Right? Because that's the rule. It's the element of whatever this number is, and then this whole thing goes to the bottom. Do we agree? But now the problem that we have is that the derivative of this piece has got to go on top. Right? So we got to take the derivative of this piece. So what I'm going to do is do d dx of this piece on top. Does that make sense? Does everybody understand what I'm talking about? Just trying to separate the two pieces, right? We've got the derivative of this log 7 first that we've taken care of by this. But then on top of that, we got the derivative of this piece. Now, what's interesting here is, and this is where, this stuff gets so terribly difficult, is, you might say to me, well, Dreyer, what about the 4? How come you didn't do the chain rule? Well, because it's not time. All right? Which is a really crappy answer. But it's just not time. Because when I take the derivative of the log 7 4x, now I'm dealing with the 4. That's when that chain rule will go. This is just the derivative of this piece on top, and now I'll deal with that. So now what do I get? Well, I don't know that I have enough room to type it there. So I'm going to go ahead down here and type it here. So the derivative of this piece. So on the bottom we have this thing. Right? And on top we have another fraction where we have ln 7 right on the bottom. We also have 4x plus 1, yes? And what we have on top? We have 4. Is that where you got to? Okay, now, how do you finish it from there? Right? Now, this is where some people go like this. You finish it by putting the pencil down, and you turn that in. And then you just pray that whoever's grading it goes like this. Close enough. We cannot leave complex fractions as answers. Okay? So this is 4 over this divided by this. Do we agree? So in essence, I could take this and put it over 1. Do we agree? And that would turn into this times this. Does that make sense? As it's a complex fraction. Okay? So that would give you a final answer of 4 over ln of 7 squared, right, times 4x plus 1 times log base 7 4x plus 1. And that is your final answer.
So when you go to multiply by the reciprocal, is it always the denominator that's the reciprocal? You can't do the
Yes.
numerator?
No. Right. Yeah. It's always the bottom number. The question was when we multiply by the reciprocal, is it always the bottom number that gets multiplied by the reciprocal? Yes. It's keep, change, flip. Keep the first, change the sign, flip the second. If you're from Kentucky, keep, flip, change. They call it KFC. Not even kidding. It's not even a joke. I'm being serious, actually.
Way to remember.
All right. All right. Any questions on that? All right. With that, we're going to move our discussion today into compound interest, okay, and deal with compound interest. Was something that actually was early on in the course. I didn't deal with it much because I like to deal with compound interest when I deal with continuous interest and just deal with them all together as one big topic, okay? So formula for compound interest works like this. You are going to we have two formulas for compound interest. It's the money that you put into an account times 1 plus R is an interest rate. R is an interest rate, so it's always as a decimal. Okay, so P is your starting amount. All right. R is the interest rate. And that should be as a decimal, please. All right. T is the length of time. All right. And N is the number of times it's going to compound. Okay, so when we talk about the number of times things compound, it could compound monthly, meaning it compounds 12 times a year. It could compound quarterly, meaning it compounds 4 times a year. It could compound annually, which is what we call simple interest, which would be that it compounds 1 time. Okay, semi-annually would be 2. Daily would be 365. Does that make sense? And then there's continuous interest, which basically just means it's always drawing interest on the interest. Every second of every half second of every day, it is compounding continuously. Okay? 2 totally different formulas. All right? Now, on the final exam, you do get a formula sheet. And on that formula sheet, you have both of these 2 formulas. So the critical thing for students becomes when they read the problem to know which formula is which and when they're supposed to use it. Okay? So here's what we're going to do. I've got some examples that I've done for you or that I've written out for you. I'm going to press pause, give you a chance to work those examples, and then we'll resume the video and work them together. All right. So we got $10,000. We're going to invest into an account that pays 6% interest. The money's left in there for 10 years. What's the total amount that you've earned? If you're going to do that yearly, you're using this formula here, okay, where yearly is N, that's 1. So the formula comes out to 10,000 times 1 plus, for the purposes of our discussion, I know that 1 plus 0.06 divided by 1 is simply 1.06, but because I'm going to change it from yearly to quarterly to monthly to continuously, I just want to leave that 1 there because I'm going to switch that around. Now, when you raise it to the power, this is the critical part. When you raise this thing to the power, we're raising it to the RT. All right, we're raising it to the RT. We're raising it to the RT. We got to put that in parentheses if we're going to type it in as a multiplication. 1 times 10. All right. We got to put that, or no, excuse me, 0.06 times 10. Give me 1 second, please. I apologize. It's P equals 1 plus R over N to the NT. I was thinking RT didn't make no damn sense. Why would you raise it to the rate? It's the number of times and the number of times you're going to do it every year.
I was getting less and less like numbers.
Yeah, yeah, no.
I was like, wait a minute.
That's-
The compounds should be getting higher.
Yeah, it should be getting higher.
I was like,
That was my apologies. I was thinking about this formula when I was typing this one. So that one is right. P equals RT. This is NT. My apologies. So this should be 1 times 10. All right. This video may never even get published. I ain't lying. All right. So it's 1.06. So the amount that you would have here is 17,908.
You don't care for the decimals?
48. Okay. Now, what would it be if you did it quarterly? What would it be if you did it quarterly? The 1 changes to a 4. The 1 changes to a 4. And it's 18,140.
Can we round up with money? Or don't we have to like round up?
You should go to the nearest penny. All right, 18,140.18. So, doing it 4 times over doing it once, you increase your interest by $200. $200. Like when you get to a point where $200 don't matter to you, give it to me. You know what I'm saying? If you're going to do it monthly, switch the 4 to a 12. Switch the 4 to a 12. Get a syntax error?
The parentheses is backwards. Let's go.
That was your fault. 18,193. Right? Now, continuously, what would you do? It's 10,000. Okay. E to the, it's 10,000. Is that 10,000? E to the, 0.06 times 10. $18,221. Does that make sense? Now, as an aside, one of the things you should probably never do, because it's very depressing, is when you buy a house, never take your monthly payment, multiply it by the number of times you got to pay it.
Just be like, oh.
Because you quickly realize you're getting really, really, really taken over the coals. All right? So suppose you, and it doesn't work quite this way, but I'll give you an idea of what it's like. You know, let's suppose that you have $150,000 that you buy a house for. Maybe you buy a $200,000 house and you put $50,000 down. Okay? $200,000 house is a pretty decent house. Okay? So you take your $150,000. Let's say you pay 3.5%. Right? And let's say you do that monthly. Right? And let's say you do that 30 years. Now, what's interesting is 10 years is not much, right? I mean, like it didn't double. Does that make sense? So in 10 years, it doesn't even double yet. You see what I'm saying? Like, after a certain point when the interest starts compounding on the interest, it's compounding on the interest, it freaking skyrockets. Does that make sense? Which is why, you know, so you generally get two cases when you buy a house, right? You can either do 30 years or 15. How much better is it to do 15?
$200,000 better.
The only problem is over 15 years, this payment's a lot more. So if you can swing the higher payment for the 15 years, you save yourself a crap ton of interest. Does that make sense? But, you know, a lot of people can't afford it if they do it over 15 years. They got to do it over 30 just so they can get the payment down to a point where they can handle it. Because not only do you have to pay the $150,000 for the house, you still got to pay taxes and insurance, which may be another $6,000, $7,000, $8,000 for you. Does that make sense? So, and that's a yearly fee as well. So, and a lot of insurance companies or a lot of mortgage companies will actually escrow your taxes and your insurance so they can guarantee that it's going to get paid. Because one thing the mortgage company doesn't want is for you to have this house that you're not paying taxes on. So a lot of times they escrow that. They just put it as part of the payment, and they say, you know, at the end of the year, we'll have enough money saved up for you to pay the taxes and insurance for you. And then next year it restarts again. Okay. But, I mean, you can kind of see kind of how that mortgage system works with really large numbers over a really long period of time. Okay. So one of the questions that we would ask now is, if I'm going to compound this $10,000, right, at 6%, how long will it take to double it? Like, what would the time be? I should have exited that. What would the time be if I wanted to double my investment? How long do I have to leave it in there for? I mean, at 6 years, or excuse me, at 10 years, it got to 18,000. So I think it's safe to say that it's not 10 years. And I think it's safe to say that it's probably longer than that. Okay? How much longer than that? Is it 20 years? 15 years? How do we go about doing that? I'm all ears.
Keep plugging in numbers until you.
So one solution, and honestly, not a bad solution, right? One solution is to go like this. You know what? Screw it. I don't know.
I got about 12 years, 20,544.
So one solution is just take a calculator and then just start plugging in damn numbers. 10,000 E 0.06 times 10. That gave me the 18,000. That wasn't enough. 11. 101 years and you'll just retire or be dead. One or the other. I mean, I don't know which will happen first. You know, so this, I mean, while it's not a very effective strategy, it's not a bad strategy, right? Just freaking plug in random numbers and then hope the one time you hit, right? 12 years, what do we get? Oh, so somewhere between the 11th and 12th year, it happens. Okay, somewhere between the 11th and 12th year. So what year is that? You know, and then you're like, I don't know, 11.6. Okay. How would I figure it out? Well, let's think about it. Would I really want, if this is my formula, and P is 10,000, right? R is 6%. And what do I want? I want to double that, yes? So how much do I want this amount over here to be? Do we agree? How do I solve that for T? Well, the first thing to do would be to divide both sides by 10,000, yes? Divide both sides by 10,000. And what do you get? How about 2? Equals e to the 0.060. How do I solve for that? Take the ln of both sides. Yes. When you take the ln of the other side, you'll just get 0.06t. The e will go away. E and ln are inverses of each other. All right. And then how do you solve for t? Do what? Divide by 0.06. So the length of time it takes for it to double would be the ln of 2. This is where you got to be careful. Don't hit divide by 0.06. Close that parenthesis first and divide by 0.06. 11.55. Let me ask you a question. Would it make any difference whether I had 10,000 I was trying to double, whether I had 100,000 I was trying to double? How long would it take to double 100,000?
I think we take longer, right? Or yeah, it'd probably take less because your interest should be higher, right?
Why would it matter?
Because you divide the same thing as double. So.
See, if you started off with 100,000, right?
You still get 2.
If you started off with 100,000, then all you're trying to do is get to 200,000. And when you divide by 100,000, what are you going to get? So whether you start with $1, whether you start with 10,000, 100,000, a million, or like Oprah money, which is just like always doubling, right? No matter what you start with, the length of time it's going to take in order for it to double at 6% interest is 11.5 years. And so if you think about it, the only thing that's actually affecting anything about this whole process is whatever the interest rate is. Does that make sense? This number ain't ever going to change. If all we're doing is doubling, this will always be the ln of 2. And that gives rise to another formula, which is the, like half-life in terms of atoms, and also doubling time, which is a standard problem. How long will it take for something to double? And the answer is it's the ln of 2 divided by r. So the time it takes for something to double and this is another formula that you have, is T equals the ln of 2 over r. Does that make sense? All right. So whatever that rate is. Now, there's a concept called the rule of 12, or rule of 72, excuse me. Okay? And kind of an investment term. And the rule of 72 simply says this: the approximate time it will take for an investment to double is 72 divided by whatever the interest rate is. So 72 divided by 6 is 12. And that's about how long it will take. So, like if I say instead of 6%, how long will it take to double? How long will it take to double at 8%? What's the answer? Well, so the rule of 72 would say it's about 9. Right? The rule of 72 says it's about 9. The actual answer is the ln of 2 divided by 0.08, 8.6 or 8.7. So does that make sense? The rule of 72 is just a guide, right? Like that's not a hard and fast, well, the answer's 9, damn it. All right? But let's look at it. If you're on a multiple choice test, and your choices are 8.7, 10.3, 11.4, and 6, then you're going like this. I don't know. It's about 9, though. All right? And that's how that works. Any questions on that? Again, please adjust the formula from earlier. It is not RT. It is NT. And accept my apologies.